Okay. So we'll continue to solve question 2b. Okay. So like I said earlier, you have a sphere, and then inside the sphere we have the charges, right? So you have charges which are packed together. So hence we can talk about what the volume charge density. What that simply means is that we are looking at the total amount of charges, right, over the volume, right, the volume of the sphere. So that's what we refer to as volume charge density. So we have volume charge density. Then from the question, we want to find the electric field intensity outside the what, if we place a point outside the sphere, right? So we know that from the diagram or from the figure, you can see that the radius of the sphere is what, a, right? And then if we place a point P outside the sphere, then we can get the radius, or we can get the distance from the origin of the sphere to that point. That will give us the radius, right, which is the same as the distance between the two, right? Now with this, we are to find the electric field intensity for the first case. So we call this case 1. We can write here case 1. That means the radius r, which is the radius of the sphere with respect to the point which we place outside, if it's greater than a, right, the radius of a sphere where the volume charge is. So we want to find the electric field intensity, or we want to find the current, or we can say one find the electric flux density which are passing through the point P which we place outside. So we have point P. So to find the electric field intensity, we use Gauss's law, right? Gauss's law, which says that the total electric flux, right, leaving a surface is going to be equals to the total charge enclosed by the surface. So based on this, we can get we are having an enclosed surface. So if electric flux density, electric flux are emanating out of that surface, we can have the electric flux density, then dot product of what, the surface vector, right, the surface that we have. Now we have to now try and then find electric flux density and then the surface vector for this. Now we have to make some take notes of this. When it comes to a sphere is considered to be a spherical object. So the electric flux density, the component of the electric flux density that is going to be emanating out of the sphere is going to be normal to the sphere, right? So in that sense, we can write the electric flux density is going to be consisting of only the components of the electric flux which are going to be normal to the surface of the sphere. So we can write the electric flux density will be equals to the magnitude times the unit vector, which is going to be what, normal to the surface. So we have this is for the electric flux density, and now we can now get for our surface vector. We want to get for our surface. So when it comes to the surface vector that we have, so we think about the fact that the flux is passing through the surface. So I have the S here, and for the surface that we have, we are going to look at, we express in a vector form. That means that we look at our surface and we look at the unit vector, which is normal to the surface. So the surface vector will be equals to the magnitude of the surface, meaning the differential surface. That's what we are, meaning we are taking a small amount of our surface. Then the unit vector, which is going to be normal to the surface, is going to be what? The radius, unit vector in the direction of the increasing radius. So we have now based on this, we can come and express this further. We know this is the same as charge. I can come and write here. Enclosed surface, I have my electric flux density. I'm doing replacement now, which is dr along the direction of the radius of the sphere dot s along the direction of the radius of the sphere. So you can see that since the unit vectors are the same here and we are doing dot product, so that will give us 1. So I can write this. We have this now, dr ds which is equals to our charge. Having done this, we can further, this is integral surface, so we can put some integral surface here. We can further simplify this. So with respect to charge, I can write this, I can put the dr outside, then I put the s equals to charge. So here we are integrating surface, and then we have the s here, meaning it will, the integral will go away. We cancel the differential here that we have. That means we have here the r, then times the surface equals to charge, and this surface area is going to be the surface area of the sphere with the radius being outside, right, with the Gaussian surface. So this becomes, so the surface area of a sphere is, you know, is 4 pi r square. So this equals what? Charge. So the magnitude of the electric flux density will be equals to charge over 4 pi r square. Now that we've gotten the magnitude, it means that so we have, now I have my dr, so we have here our vector electric flux density as a vector, which equals to what? Stand the unit vector ar. So this becomes charge over 4 pi r square times the unit vector along the direction of the increasing radius. So now we've gotten this, we can now get our electric field intensity, which is going to be equals to electric flux density over epsilon naught. Then we just have charge over 4 epsilon naught r square ar. Okay. Now that we've done this, but remember here we are having charge, right? So when it comes to the charge, we look at the charge here in terms of what? The volume charge density that we have, right? We already talked about for the volume charge density is what? Total charge over what? This, the volume, right? Yes, volume over volume. So with this, I make charge the subject. We get for volume charge density times what? Volume. Then the volume. Here we are looking at the volume of a sphere, which is 4 over 3 pi r cube, right? So this is the volume. Now that we have done this, I'll replace this in the electric field intensity formula that we just got. So I'm replacing this. Remember here, when you come, we are looking at the what? The volume of the sphere where the charges are, and it's going to be the radius there is going to be A. So here has to be A. Change this to A. So now we have this 4 pi all over number 4 pi epsilon naught r square AR. This becomes, this one will cancel here. Pi here will go away. We just have this AR square. So this becomes our electric field intensity, right? For this is when R, in that case, is outside. Now let's look at when R is what? Less than A, right? Less than A. That is when we are finding the electric field intensity inside the sphere. Now, if the same concept, meaning we have our sphere where we have packed charges. So, and with this we have radius of the sphere to be A. Now we imagine we place a point inside that volume that we have, point P, and we are to find the electric field intensity now. Now when it comes to this, so you can see that everything is going to be similar to what we just did. The difference is just going to, now when it comes to the electric flux density, it's still going to be what? The R, meaning times, meaning along the direction of the increasing radius. Now the difference with this is just going to be, when it comes to, for example, so everything will be the same. So I can even write this into be charge over 4 pi r square. Yes, so this will still be the same. Now the difference will now be in terms of what? The charge that we have, right? The charge that I have. Now when it comes to the charge that we have now, you can see that charge, we say charge is equal to the volume charge times what? The volume, right? The volume. So if my P is inside the sphere, what that means, the volume here, right? That volume is going to be equals to 4 over 3 pi r cube, right? That means it's going to take the volume of what? My Gaussian surface R. That's the one that I'm going to use. And here everything still maintained. So I have the electric flux density will be equals to, now this 4 over 3 pi r cube over 4 pi r square AR. So this again will cancel this will cancel. Now volume charge density over 3 here, and then we now have our R. So R here, this will cancel, right? So I have here to be R, and then AR. We have this as our right, that's our solution. Now again, we can find the electric field intensity now to be electric flux density over the epsilon naught. So this becomes okay. So we get this as our answer for this question, for this part that we have. Right, we get something of this for R being less than, right, when R is less than A. Okay. Now let's look at the another case whereby R is equals to A. What that means is that again we have a sphere packed with charges. We know the radius of the sphere to be A, but this time we are making sure that we are placing our point on that the same radius as that of A. So we have this. Here is R. So R is equals to A. Meaning the same thing, everything will be the same. Electric flux density will be what? Charge over 4 pi R square AR. Okay, right? Everything will be the same. But know this, because R is equals to what? Remember, R is equals to A. That means I can write the same electric flux density to be equals to charge over 4. Instead of 4 pi, R is the same thing as A, so I can write A square AR. Then now when it comes to our charge, we know our charge is going to volume charge density times the volume of the sphere, which is 4 over 3 pi. So since it's what? A, the volume of the sphere, then this one is A, 3 over 4 pi A. Right. So we have this to be AR. So we have something of this nature for this, right? We have something like this. Now with this that we have done here, so here this part will cancel. Here this part will cancel. This, you have this over 3. Here is 0 power 2. Okay. So here also be what? 3 VA AR. So we have something of this nature for R equals to A, right? So we get this. Now that we have done this, it's like, so we have gotten all our electric field intensity. Okay, now let's just get, we've gotten electric flux, and let's just got electric field intensity for this as well. So volume charge density epsilon naught, say okay, so this is so we have this. Now with this we can just make a sketch, can make a sketch whereby I can put R here. So we can see, and I indicate here A, which is the radius of what? The sphere that we have. So you can see that when this R is equals to A, right, we can put here the magnitude volume charge density, the electric field intensity, the magnitude of the electric field intensity. Then we can indicate here when R is equals to A, what do we get? The magnitude here will be what? This here. So we get this. And then when R, right? You can see when R is equals to, this is when R is equals to A. When R is less than A, what do we get? We get this one here. So I can get, yes, epsilon naught here. Okay. This part. So we get something of this nature. And then this side, we can indicate this side to be like this. Now when R is what? You can see when R is greater than A, we got R is greater than A, we got this one, right? So you can see this, as R increases, you tend to what? It approaches 0, so we get something of this nature here. So this becomes our sketch for this. So we come to the end of this video. So we continue with the question 3 on the other video. Bye bye.